Hello, my name is Akshar and I'm going over 2D magnetic materials. So why are 2D magnetic materials important? So this magnetism can be integrated into van der Waals heterostructures containing other 2D semiconductors such as graphene and 2D TMDs. And the important thing about these heterostructures is van der Waals bonding. And this is an attractive force bonding versus physical bonds such as ionic and covalent bonds. So when making these 2D magnetic materials and connecting it to other semiconductors and insulators, there's no need to match the lattice at the interfaces. So the main difference between 2D and bulk magnets is that bulk magnets have bulk and thermal effects dominating, while the 2D magnets have interfacial effects dominating. So the materials can behave differently based on how many layers there are in the material, or like what materials like next to the material are interfacing with it. So why are 2D magnetics good for spintronics? So spintronics prefers materials with less energy to change magnetization, which is true for 2D magnetic materials because they're atomically thin. And it's also an easy integration with nanostructures, which is the van der Waals heterostructures. So this is an example of a 2D magnetic material from literature. So the main thing about this experiment is that it shows that the number of layers in a 2D magnet can change magnetic behavior. As shown in the box A and C for 1 and 3 layers, it shows ferromagnetic behavior, while box B shows anti-ferromagnetic behavior for 2 layers for the most part. And the main concept that this experiment shows is that 2D magnetic materials are not just thinner versions of bulk magnetic materials. They're actually a distinct group of magnets that can be controlled by stacking and number of layers. So why is 2D magnetism non-trivial? So in an ideal isotropic system, thermal fluctuations can destroy magnetic order. But as we learned in class, magnetic anisotropy is a solution to that, as some spin directions will be preferred over others, causing magnetization to stabilize in preferred directions. For CRI3, which was a previous example, crystalline anisotropy is along the c-axis, which is perpendicular to the 2D layers. So the main result from the CRI3 experiment, which is one of the first 2D magnets, is that it showed anisotropy existing in 2D magnets, as shown by ferromagnetism and antiferromagnetism. So the main properties of 2D magnets are layer dependence, as shown by the previous experiment, and there's hard versus soft 2D magnets. So an example of a hard magnet that's 2D is CRI3, which has more stable, well-defined states, as shown by the hysteresis loop, and it's also an icing system, as spins favor to be against or with one axis. So an example of a soft magnet is CR2G2TE6, which is shown by this hysteresis graph. And it's easier to change state, and it's usually a 2 or 3 axis system, as the spins can rotate more freely. So this is another example of a 2D magnet, which is metallic and is an electrical conductor. And this type of material is very useful in nanodevices and spintronics, as it is both a magnetic material, specifically a ferromagnet, and it's also an electrical conductor. So it can actually conduct current too. So it can be useful in MTJs and other devices. So the problem with this magnet is there's a very low operating temperature, which is about 10 Kelvin, as shown by the first column in the graph. However, as shown by this experiment, applying a gate voltage can cause ferromagnetism near room temperature at about 240 Kelvin when about 2 volts are applied. So what this experiment shows is that there's electric control of ferromagnetism, and this is also a major step towards low-power magnetic devices, because 2D magnetic materials need much lower power than bulk magnetic materials. So this is from MUMAX. So in 2D magnetic materials, you can also control domain wall motion within the 2D film with 1D channels or tracks, which have much lower domain wall energy. So in the MUMAX simulation, what I did was embedded 1D magnetic channels in a 2D magnetic film by locally modifying parameters such as the exchange stiffness and the anisotropy to guide domain wall motion. As you can see in the picture, there are 3 tracks. So the domain wall energy and width dependence on material properties are energies proportional to the square root of exchange stiffness times anisotropy, and thickness is proportional to square root of exchange thickness over the magnetic anisotropy. So this results in the channels with channels with higher exchange stiffness and much lower anisotropy results in lower domain wall energy because the change in Ku is like much greater, and also a thicker domain wall. So this results in a non-uniform domain wall, and the domain wall motion within the channels advances much farther than outside the channels. So these channels can provide preferred pathways for domain wall motion, and they can be applied in low power and guided information transport and spintronic devices. So this is how 2D magnetic materials can be applied in MTJs. So what an MTJ is basically two ferromagnets separated by an insulating layer, and then the resistance depends on whether the magnetizations of the two layers are parallel or anti-parallel. So a property of 2D magnets that's very useful is spin filtering. So actually, this is just for any magnet. So spin filtering is magnetic layers preferring to transmit electrons with one spin orientation more than the other. But for 2D materials, tunneling current is extremely sensitive to magnetic configuration, as tunneling current is what goes through an MTJ. So using a single versus few layer magnet for the ferromagnetic layer can vary transport strongly through an MTJ. Also, the scalability of 2D magnets is very important, since the ferromagnetic layers will only be a few layers thick, so the MTJs and other surrounding electrical components will take up much less space in devices. So there are three main challenges for 2D magnetic materials, and the first challenge is a low operating temperature. So as seen in one of the previous experiments, there's research currently being done to fix this with electrical gate biasing, bring the operating temperature to about 240 Kelvin, which is approaching room temperature. But this only when about 2 volts are applied. And however, this is not like the ideal solution, as it'll take a lot more power. Also, there is another challenge is environmental and chemical stability, because since van der Waals magnetic materials are sensitive to air and other effects during fabrication, the ideal magnetic properties that were decided upon when designing the device will slowly degrade after each fabrication step. So one of the solutions found through research is encapsulation, but it's very hard to do for manufacturing scalability. So they need a process engineering solution for this. Also, 2D magnetic materials are sensitive to defects because in bulk magnets, defects only cover a very small volume of the entire lattice, but in 2D materials, defects will cover a significant amount in the area. And as seen before, the amount of layers and even like small structure defects can cause magnetism to completely change. And this is a big problem for reproducibility in 2D magnets, as each magnet will have a different property. So the future of 2D magnets has been divided into two main areas. So one is just improving the magnetic materials. This means increasing the operating temperatures towards room temperature, as seen in the previous experiment. And this can be done in two ways. You can either search for new magnetic materials, which has like a never-ending process, or electrostatic control of previously discovered 2D magnets, such as Fe3Ge Te2, which was one of the previous experiments. And the other way that the 2D magnetics research is going to is improving the structures, since interface interactions are the main ways that the properties of 2D magnets can be changed. So this includes studying the behavior of 2D magnets when placed to a conductor, insulator, or any other material in the van der Waals structure. An example of this is a 2D magnetic material providing spin selectivity in a heterostructure, and other materials in the heterostructure causing conduction and everything. And these are my references for the experiments and images.